Having a large mirror is only part of the issue in astronomy if you want to see further and deeper than ever before. As we realize, the atmosphere imposes a limitation on all ground-based telescopes. The diffraction limit, or the sharpest image a telescope can make, is proportional to the aperture. Bigger mirrors make sharper images, but this is mitigated by the blurring effects of the atmosphere, such that every mirror more than about half a meter across is limited by the blurring of the atmosphere and can never realize its full potential. Until 5 or 6 years ago, this was a fundamental obstacle to astronomy. But now astronomers have perfected the technique called adaptive optics that allows them to essentially cheat the atmosphere and recover the full diffraction-limited images, the sharpest images possible, from their large mirrors. Here's how to imagine what's going on. Out through the vacuum of space, light from an astronomical object arrives with its wavefront absolutely plain, smooth, and uniform. As that wavefront reaches the upper atmosphere, it starts being jumbled. The light essentially moves at slightly different speeds, corrugating the wavefront and producing a blurry image. Not only that, but the image changes its shape and nature dozens of times a second because of the rapid fluctuating motions and turbulence in the upper atmosphere. It seems that it would be impossible to correct for this, but the techniques have been developed quite recently that allow astronomers to do just that. Adaptive optics was first perfected at slightly longer wavelengths than the eye can see, in the near-infrared, or 2 microns. If you look at a dense cluster of stars, in this case at the galactic center, without adaptive optics, the blurring of the atmosphere bleeds the light from all the stars together into a big mess. If you could somehow correct for the turbulence, the stars would sharpen up and they would all become individually visible, also allowing you to see much deeper and fainter than you could see without the correction. How are these corrections actually made? Well, you don't do it with the primary mirror. The primary mirror, remember, are 6 feet or 8 feet across, and there's no way to change the shape of a large object like that dozens of times a second. But each of these telescopes has a secondary mirror, which is only about 1 meter across. This mirror, in practice, is made of a very thin material, usually beryllium, only a millimeter thick, and it's actively supported on actuators, hundreds of them, on the back side. These can be adjusted many times a second to change the shape of the secondary mirror. So the atmospheric turbulence is subtracted out at the secondary mirror itself. For the large binocular telescope, the secondary mirror is about 1 meter across. These are exceptionally fragile things, 1 millimeter across. They cost about $1 million, and we have actually broken one. They're very hard to work with. But these are the essential ingredients for making the full power of your large optical collecting area. The secondary mirror also needs an exquisite optical surface. It has to be accurate to about 1/10 of the wavelength of the light that's being imaged, which is very small, tens of nanometers. Here's the impact of that kind of correction. Remember, the typical blurring of an image at a ground-based observatory without correction is about 1 second of arc, or maybe half a second of arc at a very good site like Chile or Hawaii. If you had 2 stars on the sky separated by much less than half an arc second, there's no way you could tell them apart without this correction. But when you add the adaptive optics, real-time correction of the wavefront, you sharpen up the images to the diffraction limit of your telescope and easily resolve images with this separation. The most dramatic evidence of the power of this technique comes when we look at an image of M92, a globular cluster, taken with the Hubble Space Telescope and our ground-based telescope using adaptive optics. These images have been corrected for the different light gathering power of the 2 facilities, so it's a fair comparison. You probably can't tell which is taken from space and which is taken from the ground. In fact, the left image is the Hubble Space Telescope image, which is actually slightly poorer than the ground-based image with adaptive optics. In other words, the historical advantage of space over ground in terms of sharpness of the image has been fully overcome by this technology. In late 2012, using the adaptive optics technique, we obtained the sharpest image ever made of an astronomical source using the Magellan 6.5 meter telescope in Chile. A group led by Laird Close, one of my faculty colleagues, did this work. The Airy pattern is the purely theoretical image that would be formed by an optical telescope of this size in the absence of any atmosphere. When modeled in a test tower, it's also a fairly pure point spread function because, again, there's no real telescope looking at real sky. Normally in Chile, the image size might be 0.7 or 0.8 arc seconds, a fairly large blurry mass at this scale. But when the adaptive optics is turned on, the image sharpens to very close to the fully theoretical resolution of this large mirror. We have essentially recovered the full optical capability of a glass piece this size as if the atmosphere were not there. What does that mean? Well, the Hubble Space Telescope's maximum angular resolution is about 70 milliarc seconds, or 70,000th of an arc second. The image you're looking at has a resolution of 25 milliarc seconds, 3 times better than the Hubble Space Telescope. The fundamental obstacle to making sharp images with ground-based telescopes is the atmosphere. In the last decade, and particularly in the last few years, that obstacle has been overcome by the use of adaptive optics. This uses the secondary mirror, a very thin form that can be adjusted in its shape dozens of times a second, to exactly compensate for variations in the wavefront that arrives from space due to turbulent motions in the Earth's atmosphere. The result of this clever ingenuity is that ground-based optical imaging now surpasses imaging made with the Hubble Space Telescope.